with support from the Climate Kick Alumni Association. Welcome to The Elephant.
For the very first time in the history of Homo sapiens, we are asking people of different cultures in different continents to agree.
Climate change is a fact.
All the evidence suggests climate change
The coastline of South Florida is going to be pushed considerably inland.
Make food,
Our
take
politics.
everything.
Extreme events will be the new normal.
About
Climate change.
climate change.
Climate change. Climate change is to blame.
No one is addressing it.
Time for talking is gone. We need hard action. It is the elephant in the room that we don't want to talk about.
The elephant.
Hello, I'm Kevin Caners, and welcome to The Elephant. This week on The Elephant, we're doing something a bit different. We're bringing you a special live interview. Last week, we were at a Climate Kick event in Birmingham, England, called the Innovation Festival. And while we were there, we talked to renowned glaciologist Martin Siegert in front of a live audience. Now, Martin Siegert is the co-director of the Grantham Institute for Climate Change at Imperial College in London. But the reason we were interested in talking to Professor Siegert was because of his work on glaciology. He's devoted his career to researching and studying ice and seeking to understand the way it behaves. And he's put a particular focus on Antarctica, a place that's been drawing increasing attention from climate scientists. Antarctica's ice sheet is upwards of 3 to 4 kilometers thick in parts, which is so much ice that if it was to melt completely, it would mean dozens of meters in sea level rise. In other words, it's important that we get a handle on how the frozen continent is changing. Martin Siegert has visited Antarctica now 3 times. His most recent trip, in 2012, was for an ambitious research expedition to explore a gigantic subglacial lake called Lake Ellsworth, one of upwards of 400 lakes that are buried beneath the ice sheet and which have been sealed off from the rest of the world for potentially millions of years. During our interview, we spoke about the ways in which scientists study Antarctica, how the ice sheet is changing, and why it matters even for those of us living far away from the poles. Without further ado, let's head to Birmingham for my interview with Martin Siegert. Okay, thanks so much for everyone coming out. So just a quick introduction. Professor Martin Siegert is the co-director of the Grantham Institute at Imperial College London, a world-renowned center for climate change and the environment, which brings together diverse expertise on economics, finance, geography, the environment, and politics. Previously, he was at Bristol University, where he was director of the Glaciology Center, and before that, he was head of the School of Geosciences at Edinburgh University. In 2013, he was awarded the Martha T. Muse Prize for Excellence in Antarctic Science and Policy, and I'm very happy to have Professor Martin Siegert here with us today. Thanks for coming.
Thank you.
Yeah. So I maybe just wanted to start by asking you, how did you get involved with glaciology? How did this interest develop?
Yeah, well, many scientists that you might speak to will have a good story to tell about how they got involved in specific areas of science. I don't really. So my background is pretty normal, like many people. At school, I was interested vaguely in the planet that was around me. It's the 1970s and 80s, right? So it was a different time to now. I was interested in the planet around me. I was brought up in a little town 40 miles north of London. It was, I guess, pretty sleepy, nice cosy existence. And I had no ambition at all to get into science. None of my family had ever been to university. I had no expectation about what I would do in my career at all. I was simply sort of chugging along, going year to year in my school days. Pretty good at maths, good at physics, like geography. That was it. And then it came to university, and I had really no idea. I mean, at that stage, if someone was going to ask me, what do you think you're going to do as a career, I'd probably say something like, be an accountant, because that's pretty much what I knew about. You know, the people I know.
If you're good at maths.
Yeah, right, good at numbers, so to do that. And I was advised maybe you want to take a course in geography or something like that. And I suddenly started thinking about geology as a course, and read some information in prospectuses, university prospectuses about that. Knew nothing about geology, was never taught about that at all. Reasonably interested in rock formations that I'd observed on holidays and things, but never really gone into any detail. And as part of that learning took place, I discovered the subject of geophysics. Now, geophysics is another very enabling subject, and to do it, you need maths and physics as a background. And in the area that I work in climate science now, when you talk to other climate scientists, they're all geophysicists, or one way or another. Anyway, so I did that, and got a reasonably good degree. It enjoyed my time, and but then I took some time out from my degree, and I decided to do that. But I needed a job. You can't, taking time out. You can do some things when you take time out. Go around the world or something. Well, I didn't do that. I ended up for a year working in road construction as a labourer.
Just as exciting as world travel.
Yeah, you're right. I tell you what, after you've done it for a little while, you do appreciate having an office job or something like that, because it was quite strange. My hands aren't suited to manual labour, right? People I was working with were commenting on my hands not looking like theirs, and their hands didn't actually look like hands anymore. So I didn't want my hands to look like this. I had to wear gloves, using a lot of concrete, and it's quite a caustic substance, and I was wearing gloves all the time. There was quite a lot of Mickey taking about that, and I did that for a year, and I was really pleased to do it. It was hard work. It's being outside in all conditions. People are getting paid on how much work they do. They're not salaried, and it's a side of life I had no idea about, and I'm really grateful for having done that for a year. And every time I go back to the road that I constructed, a little road in Suffolk, and every time I see some roadworks, you don't have to go far out of this conference venue to see roadworks in the centre of Birmingham right now. For me, it's very interesting, because although things have changed a lot, right, in climate science and the world around us, road construction hasn't changed much at all, right? So it's very familiar to me.
And so was glaciology your escape from road construction?
Yeah, because I knew I wanted to do something else, and I didn't know whether that was a job or anything, but I was pretty open-minded, and I was sort of hedging my bets in lots of different applications, and I was getting a few job offers here and there. It wasn't quite right for me. And then I was reading in the New Scientist or Nature or something like that, an advert for a PhD in glaciology, and I hadn't done no glaciology at all, none. I hadn't studied ice in my degree, hadn't studied the ice age in my degree, and this particular PhD was for someone to know about glaciology and work out what the ice sheet in Europe was like at the ice age. But the skills that were needed were geophysics, maths, and physics, and that's what I had. So I didn't have any knowledge about the topic, but I had all the skills that were needed. And like several things that I've done before then and since, and I think it's advice that I would give anybody, sometimes you just have to take a chance and go for it and see if it works out, and be open-minded about things. And if it doesn't work out, then chalk that up as experience. And so I did that, and here I am. Some years later, it was a great thing, and I just glaciology was clearly a discipline that I was well suited to. I just never knew it.
And who knew that it would be changing as much as and vital as it is today?
Well, very good point. I mean, so whenever you hear about climate change on the TV, the first image you'll see is one of two images you'll see: an iceberg carving off the front of a glacier with a big splash of water, or a little polar bear standing on a sea ice floe, desperately clinging to the last bit before it all sinks. Yeah. So ice is everywhere. Ice gets into everybody's living room almost on a daily basis, certainly on a weekly basis when climate change news is put out there.
So, I mean, you just mentioned ice is such a central thing in our understanding about climate change. It's kind of the symbol of climate change. And I think we all understand why it matters, why it gets so much news. We hear about the melting alpine glaciers. We hear about the ice sheets in Greenland and Antarctica as being a really serious risk because of rising sea level. But it was also interesting when I was preparing for the segment to learn that it was because of ice, because of glaciers, that we first started to understand that climate had been different in the past in the first place. Can you tell me a bit about those findings?
Well, we have to go back quite a way. So the middle of the 19th century, the world that was around us at that time was a remarkable thing, of course, and it was sort of the same type of landscape that we have right now, obviously, but people's explanations for the landscapes and the sediments and the geology and all those things were pretty much dictated by, in the Western Europe, that is dictated by what was written in the Bible. So a lot of sediments, loose sediments that are deposited in upland mountain regions and all across other parts of various countries are in geological maps are referred to as drift. And drift is a term that is derived from the idea that when Noah's flooding happened in the Old Testament, sea level rose as a consequence, and lots of icebergs were drifting around various countries and depositing their sediment over land. So the fact that we've got sediment in lots of places was explained as a consequence of the biblical flooding. And in fact, it almost sort of was used to reinforce the idea that there is evidence for that particular event.
And if you're Republican, maybe still does.
Maybe it is. Maybe I should say. Maybe there may even be people in this audience who think that. But the important thing is that there were people at that time who were challenging orthodoxy, and there were the new scientists that were emerging, geologists that were coming out, thinking that actually these landscapes that we're seeing in front of us, in particular in the Swiss Alps and a person called Louis Agassiz, but also in Great Britain with William Buckland, we're looking at striations on rocks. So we're looking at classic upland geomorphological features like U-shaped valleys and all those sort of things, and then going to the Alps and seeing those landscapes actually being created and eroded right now by the action of glaciers, and then going back to the same landscapes in Scotland and other places and thinking, well, the only thing that's different between the Swiss Alps at the moment and these other places is there's no ice in these other places. And so there must have been ice in these formerly glaciated landscapes. And the fact that it's not here anymore means the climate has changed. And then this whole idea about there having been an ice age in the past started to take hold. And then we started getting interested about, well, if that's true, what caused that ice age? What was the cause of it? And early work was talking about the orbital variations of the Earth around the Sun. And there were 3 times that particular hypothesis was put forward. One by James Kroll, who was a self-taught mathematician from Glasgow, who had the first idea that actually the Earth orbits around the Sun in a very predictable way. And because of that variation in the way it orbits around the Sun, you get changes in the amount of heat coming into the Earth as a consequence of that variation. And he did the calculations, because it's very easy to, well, it's not easy, but you can prescribe it mathematically quite precisely. And he did that, and he worked out that with these variations, that would be enough to cause ice ages. But he got his calculation wrong. No, he got his calculations right. He got his idea about glaciology wrong. And it was this unfortunate fact. He believed that ice ages occur when you have cold winters because the snow built up. But unfortunately, that's not true. What happens is ice ages happen when you have cold summers,
right?
Because it doesn't melt. And that's the thing that he didn't get right. Milutin Milankovic, 40 years later, and incidentally, he died totally unfulfilled. No one believed his theories. He was a fellow of the Royal Society. He had this great accolades and things, but this one theory he stuck to, and when he died, no one believed it. Right? Milutin Milankovic, a Serbian mathematician, picked up the idea, but he also had this idea that actually it's the cold summers that are important. So he readjusted the calculations, and he came up with a much more plausible idea of the ice age being at 20,000 years ago, which it is, or was. But he also died with no one believing any of this stuff. And that's because the changes in the solar insolation that you get between like the maximum and the minimum type of variation is very small. It's a few percent. And people are saying that can't possibly be enough to cause these massive ice sheets to come and go. And of course, the thing that they're forgetting is there are amplification factors involved here and carbon dioxide, which we'll come to in a minute. The thing that clinched it, and this is the third way that it was put forward, was by sedimentologists that were looking at in the bottom of the ocean at the sediments, and they were noticing that in the buried shells of dead organisms, you could measure the oxygen isotope content in those shells in a temporally coherent way. That is, oxygen has 3 isotopes: oxygen 16, 17, and 18, and 18 is heavy, 16 is light. So if you have a bucket of water and you evaporate it, the evaporation will be enhanced with oxygen 16 because it's easier to evaporate. And so when you do that, the water gets enriched in oxygen 18 because it's more difficult to a lot more things than that. But for the sake of this brief discussion, that'll be fine. So the same thing happens when ice sheets form. The water from the ocean evaporates, it dumps itself on the land, and that ice is enriched in oxygen 16. The ocean becomes enriched in oxygen 18, and anything living in it, the calcium carbonate shells, the oxygen in that calcium carbonate will contain that same signature.
Right, so seeing the different levels, you can understand.
And then when you spot that and you work out how old those sediments are, And then you think about, well, actually, we can trace this oxygen isotope variation. That must be due to ocean volume changes and therefore ice sheet waxing and waning. What is the periodicity of those things? And you do a simple calculation of what is the periodicity of this change. And it's 100,000 years, 40,000 years, and 20,000 years. And those are the exact periodicities that Milankovitch had calculated as the orbital variations around the sun. And that is it. So we know. But it's not enough in itself to cause the ice ages. You need amplification factors. And that is where greenhouse gas modification of our climate is now known about. So that early work in understanding ice ages is really helping us, is a platform really for us to understand modern climate change.
And so glaciers first told us that climate change is coming about, and now, of course, today it's a big risk factor. Now, I think we think about the Antarctic and, we're told ice flows, but of course it's hard to actually get a sense of it being this dynamic thing. Can you give us a sense of the Antarctic and how much is actually going on there that we can't actually see at the surface?
Well, I'll give you some facts and figures about it. So there's enough ice in the whole of Antarctica to raise sea level globally by about 60 meters. Most of that is in the East Antarctic ice sheet, about 57 or so meters worth of ice in East Antarctica, about 3.5 in the West Antarctic ice sheets. But they have different ice sheets. In West Antarctica, the ice, which in both ice sheets, the ice is 2, 3, 4 kilometers thick. In West Antarctica, the bed of that ice sheet is suppressed significantly below the level of the sea, in some places more than 2 kilometers below sea level.
So you mean the actual continent is below sea level?
Yeah, that's right. And the ice is resting on the bed. It's grounded, but it's significantly below sea level. So in one hand, it's already displaced quite a bit of its own weight in water, you might think. And that's why as a volume of ice, when you melt it, it's not the volume that causes the sea level rise, it's the amount that's above the level of the ocean. So it's only 3.5. It's about 7 meters worth of ice that's there, but it's about half of that is already displaced right now. So we're particularly concerned about Antarctica because, unlike in Greenland, which is actually actively melting on the surface right now, you can see, you fly over Greenland or something, you see pools of water on the surface, and in some years most of the surface of Greenland ice sheet is subject to some level of melting. But there's hardly any surface melting in Antarctica. There is a little bit, but it's really negligible compared to other things.
So if you look at it, it looks like nothing's happening really.
Well, it's indeed, and it's the warm ocean that surrounds Antarctica that is causing the problems. And with ocean warming, both historical ocean warming and what's happening now and in the future, it's that warm water getting in contact with that ice sheet that is causing the ice loss that we are observing right now with satellite altimetric measurements.
Right, and so this is because the continental bed is actually below sea level, that the ocean water can contact the bottom of the
Indeed, that's exactly
ice
right.
sheets.
And it's referred to as a marine-based ice sheet. So it's not on land. Most of East Antarctica is on land. Some of it isn't, which I'll talk about in a second. But most of the West Antarctic ice sheet is suppressed below sea level. Some of it isn't, but most of it is. We're also worried about East Antarctica, and that's because it's an order of magnitude bigger than West Antarctica. And so any changes that go on in East Antarctica only have to have, about 1/10 of the same activity and the same amount as in West Antarctica for it to cause the same effect of sea level change. So, and in fact, you might even notice it. You would notice quite a big effect happening in West Antarctica, but to have the same amount of sea level influence in East Antarctica, you might not even notice things going on. It's such a big ice sheet. So we're worried about that as well.
So I think a lot of us who follow climate change will remember about a year ago when that NASA study came out that first said what sounds like the West Antarctic ice sheet is headed for irreversible collapse. It might take a long time, but it seems like it's heading for collapse. What was the actual new data that allowed us to understand that?
Yeah, we've known about West Antarctica being vulnerable to what's called marine ice sheet instability, and that is as the ice melts and the grounding line, which separates the grounded ice sheet from the floating ice shelf, as that grounding line.
So where the ice sheet actually is supported by land, basically.
Yeah, supported by land or floating in the ocean. That transition is the grounding line, and as that retreats. If it retreats into deeper territory because of the topography, that's an unstable situation. It's going to encourage accelerated ice loss. And of course, so much of the West Antarctic bed is below sea level. That's why we think it's particularly vulnerable to change. Now, that was hypothesized in the 1970s by John Mercer. He talked about this weak underbelly of the West Antarctic ice sheet from some rudimentary measurements that had been taken at that time of ice thickness. Didn't know an awful lot about the size and shape of the West Antarctic ice sheet at that time, but even with some basic measurements, he was able to make that hypothesis. Unfortunately, that hypothesis is now testable with other data that we have with satellite altimetry. And it turns out that there is an area of the West Antarctic ice sheet around a place called Pine Island and Thwaites Glaciers and the whole of the Amundsen Bay sector, so it's a whole sector of the West Antarctic ice sheet, that is losing considerable amounts of mass, and the ice sheet is lowering in a measurable way with the satellite information that we have right now. And what it's pointing to is this influence of the warm ocean melting the edge of the ice sheet and the ice sheet reacting to that. What Ian Jockin and Eric Reno pointed out in papers last year was that this could well be the first signs of this marine ice sheet instability. And if that is the case, there may be nothing we can do to stop it.
And that would mean, would that mean all 3 meters of the West Antarctic ice sheet?
Well, that's a very good point. So these, when you talk to scientists, they're very keen to point out the limitations of studies and the more work that needs to be done. When you talk to an audience like this, it's kind of, we don't want to do that necessarily because it's important to state what the problems really are. But I think it's fair to say that the way that glaciology works is that ice sheets are divided up into sectors, and each sector may operate in a slightly different way. What the knock-on effects of the Thwaites and Pine Island glaciers retreating are going to be for the other sectors is an important question. And it turns out that the Pine Island glacier is fairly largely contained within a sort of topographic valley. So if it retreats, its retreat is going to be constrained by that subglacial topography. But in Thwaites Glacier, that's not the case. There's an extremely large, deep basin that Thwaites Glacier is going to be retreating into. And if that is accelerated ice loss through that deep trough, it may well be that the whole configuration of the West Antarctic ice sheet will change, and then we're into sort of an unknown, quite how the West Antarctic ice sheet starts behaving in that situation. I guess there are some caveats. Firstly, we need more information about the bed topography, and we might come to that later, of course, and that's very important. And we also need numerical modelling to try and understand when you have a chunk of the West Antarctic ice sheet that comes up, how does the rest of it behave? It's also worth noting that we need to talk about timeframes over which these changes might occur as well. And we can look back in geological and glaciological history in the Ice Age and how quick can you actually melt an ice sheet, and you do need centuries or even millennia to do that. But as I said previously, if the hypothesis that John Mercer had come up with has now been proven, then the changes that we're seeing in Antarctica may well be irreversible.
So how do we actually study the composition of Antarctica, like how deep the ice sheet? So you mentioned satellite measurements. Can you explain how that works? And we use planes as well with radio waves? Yeah,
it's worth noting that it wasn't so long ago we knew very little about the Antarctic ice sheet. We had the history of Antarctic exploration, which is something I've been interested in for a little while, really kick-started in 1957 and 1958, where there was an international geophysical year. It was just after the Second World War. There have been lots of developments in technology. When we talk about war, what is it good for?
Developing computers and planes, I guess.
Yeah, that's right. And scientific instrumentation, as it turns out. And it's true that geophysics was a major beneficiary of some of the techniques in radar, for example, that was developed in the Second World War. And it just so happens that ice, when it's particularly cold, say minus 10 degrees centigrade, is virtually transparent to very high frequency radio waves. So if you have a radar, like the sort of radar you would have in air traffic control, but rather than point it up into the sky, you point it down into an ice sheet, those radio waves pretty much go straight through the ice. But they rebound and reflect where there's a change in the electrical properties, a sharp change. And so the electrical properties of ice are very different to the electrical properties of rock or sediment or water, and so you get a radio wave reflection from the base of the ice sheet. And before we knew about that, we were using seismics to determine ice thickness, and seismics is a pretty good way to get ice thickness measurements as well. But to get a really good measurement, you have to dig a borehole 50, 60 meters, something like that, set off your charge like an explosion, and then another borehole where you might put your seismic receiver, and you set off your explosion, and the two-way travel time of that sound wave is, the sound wave goes down, it gets reflected, you measure the difference in time between when you set the charge off and you receive the sound, you know the velocity of the sound in ice, and you can work out what the ice thickness is, right? Great. But that takes about a day to do. The whole experiment takes about a day to do, because you've got to drill those holes.
And you have to get there.
Well, you've got to get there for sure. That's true. But if you use radar, and you put a radar on an aircraft, you can get a measurement every second, if you wish to. And you can fly your aircraft at 200 kilometers an hour, right? And you're getting instant coverage. And when that was done in the 1960s, this whole technique was developed, it increased the rate of data acquisition of ice thickness and bed topography in Antarctica by 5 orders of magnitude. It was one of these amazing incidents in physical discovery of our natural world that many people don't know about. But in the 20th century, in terms of things that really made a difference, I would rate that as being one of the most significant. I mean, I might even rate that as being as important as the marine chronometer or something, in terms of the latitude prize and understanding where you were. We discovered in the 1970s 40% about the base of the Antarctic ice sheet through that type of technique.
So instead of one day just getting one point, you can fly over a whole giant area.
Whole thing, and thousands, hundreds of thousands, millions. I mean, now we're flying aircraft in many places. But it's interesting to note that right now, there are still 2 places in Antarctica that you can stand on the ice sheet surface. And we know a lot about the ice sheet surface because of satellites. We're talking about what's underneath the ice sheet. There are 2 places you can stand, and you can be 200 kilometers away from a single point of data about what's underneath the ice. So there are 2 regions the size of Scotland in Antarctica that we know absolutely nothing about.
Those have an interesting name. The poles of ignorance, is it?
Poles of ignorance. There are 2 of them. That's right. And but there were plans coming up this coming Antarctic season to fill those. So I'm involved in a program with American colleagues and Chinese colleagues and Australian colleagues. We're going to, not me personally, but we're going to one of those places called Princess Elizabeth Land to fill in that. And there's another team that's going to the Bailey-Sessa region to fill that gap. So maybe in a year or 2, we'll have our first complete coverage. But it's true to say, it's absolutely true, that we know more about the surface of Mars than we do about the underside of the Antarctic ice sheet.
In terms of that topography?
Yeah. And it's also true to say we know more about the surface of half of Pluto than we do about the underside of the Antarctic. Well, it's true from a couple of months ago.
Because of the flyby?
Absolutely. Not the other side of Pluto, but the side that we've got measurements of. And it's so fundamental, understanding the topography of the Antarctic ice sheet, to our ability to model the ice flow. I mean, the way that the ice flows, it's affected hugely by the topography underneath. And so it's a crazy situation that we have all the techniques available to get a proper, thorough coverage of Antarctic topography. We've got every reason to want to do it, and yet still right now we don't have it.
I just have a quick question. For flying across Antarctica, I mean, where do you actually take off and land from? Do you have to fly from South America?
It depends what aircraft you use. So in the 1970s, there were very long-range aircraft were being used. Hercules C-130 transporter aircraft from the US Navy, and these are great big things with antennas on the wings, and they're ski equipped. But you pretty much have to land.
So they could actually land on the ice sheet.
You absolutely land on the ice sheet, usually with a groomed skiway, so not a bumpy part of the ice sheet. If you use another aircraft, a Twin Otter, which is a twin turbo prop aircraft, again ski equipped, you can land that on the pretty rough glacier ice, and so you can deploy that Twin Otter into deep regions. If you use a C-130, you've got to be based on the edge of the ice sheet. You fly into the middle as you take measurements as you're doing it, and you fly back again, back to the station, McMurdo Station, whatever it is. If you use a Twin Otter, you can be deployed on the ice sheet and have a little camp and do your survey and come out. And there were pros and cons to both of those. There's an intermediate version, which is a Basler aircraft, which they've all got very interesting histories because you don't make Baslers anymore. They're all reconverted old Dakota aircrafts. And everyone knows that anything about aircrafts. Dakotas are DC-3s. And DC-3s are old aircraft. The one that we've been using in Antarctica a fair bit was first bought, so the serial number of its frame was first bought by the Canadian Air Force in 1942. It almost certainly was involved in the D-Day landings, right, and the Allied landings. And these aircraft were used for parachuting people in, paratroopers and things, and they were used to send paratroopers into Arnhem, that ill-fated attempt to defend a bridge, hence the Bridge Too Far film. Some of these old aircraft have got bullet holes in them.
And they're still flying?
Patched up. Yeah,
okay, that's good.
But of course, this one, the one we're using, doesn't have. But they've got new engines, avionics. Everything's completely different. The frames are the same, and they're wonderful to work with in Antarctica. They are ski equipped as well, so you can land them. They're a medium range aircraft, so you can still fly from the edge into the middle at much less cost than a C-130 Hercules aircraft. But they're amazingly durable as well. So they're sort of good workhorses for this type of work in Antarctica.
And so when they first did those flyovers in the 1950s or 60s, was there anything that was really surprising about what they found?
No, we knew absolutely nothing about parts of the Antarctic ice sheet. I mean, doing this type of work, you get a bit blasé about it when you. This won't be possible in maybe just a few years' time. We fly aircraft into parts of the Antarctic ice sheet where we know nothing about. It's pure exploration. And you look at the oscilloscopes and the images and the data that immediately comes back, and you see, well, we're seeing mountains and valleys that no one has ever seen before. It's like an amazing thing, and you get a bit punch drunk about it all because you just don't see it for its sort of true value. Oh yeah, another mountain range that we just discovered. Just write that down. What they found in the 1970s was all of that thing, but one thing that surprised them was the presence of a lot of water underneath the ice, and in particular, certain pockets of water which can only be described as lakes underneath the ice. And some of them are maybe 10, 20 kilometers in length. They're unmistakable in the radar survey. You've got rough topography and hills and valleys, and then like a mirror-like flat surface, which can only be from an ice-water interface. And of course, the very big Lake Vostok, which is 250 kilometers long. It's 50 kilometers wide. It's one of the 10 largest lakes on the planet.
10 largest lake is under the Antarctic ice sheet.
Yeah, it's like 7th largest by area. I'm going to get this slightly wrong, something like that, and about 4th largest by volume, something like that. And it is in the middle of underneath the East Antarctic ice sheet.
Wow. And so this is actually an area that you've personally done a lot of work in. I mean, first of all, why would there be lakes underneath the ice sheet? But why isn't it just ice?
Yeah, well, in some parts, of course, it just is when the ice is frozen to the bed. But in about half of the ice sheet in Antarctica is actually melting at the bed. And you don't need volcanoes, although there are some volcanoes in Antarctica, you don't necessarily need volcanoes. You just need background levels of geothermal heating, type of geothermal heating that you get in Birmingham, which is around about 50 milliwatts per metre squared, to put a figure on it. And if you have an ice sheet, ice is an amazingly good insulator of heat. So if you have ice which is 3 kilometres, even though it's really cold at the surface, because of that really low level of background geothermal heating, it's enough to warm the ice up as you go down and down and down. And by the time you get to 3 kilometres, you'll be at the pressure melting point, which would be about minus 1.2, minus 1.5 degrees centigrade. When you get water developing underneath the ice, it starts flowing under gravity and under the pressure burden of the ice. And just like on the surface of the planet, it will start collecting in topographic hollows or where it's suitable to collect. So the fact that they discovered it, and we're really surprised about it, it's one of these, a lot of discoveries are like this. When you see it, it's an amazing thing that it's just been discovered. And then you sort of think about what you just observed and think, well, actually, yeah, of course, there should be loads of them around. And of course, the first inventory of subglacial lakes in 1973 had 17 lakes in mostly East Antarctica. We now know, using exactly the same techniques that were used in the 1970s, that there were just over 400 subglacial lakes in Antarctica, and they're scattered everywhere. The interesting thing, of course, about subglacial lakes is, well, they were, in the 1970s they were first known about, but no one really took much interest in them until the 1990s. And that's when the study on Lake Vostok took place, which I was just out of my PhD. I was sort of a young postdoc, and I was working with some very senior retired glaciologists from Russia and from the UK, who each had a data set that individually didn't really mean too much, but when you pushed it all together, they meant a lot. One had collected the radar data, one had collected seismic data from the site, and one had some new satellite data and everything. And when you put all these things together, it turns out that the seismic data collected in the 1960s, although they knew nothing about the lake at the time, was located at Vostok Station, which is at the southern extreme end of Lake Vostok. And what the seismic data showed, the seismic data were collected to get ice thickness. What they showed also was after the reflections from the ice sheet base, there's a load of other reflections that were just ignored, and they didn't know what they were. They weren't interested in those other reflections. And it turns out those are reflections from the bed of the lake. And when you look at the separation between the base of the ice sheet and the base of the lake, it turns out that that water depth is 500 meters. So beneath about 3.7 kilometers of ice, there's a lake, Lake Vostok, which is 250 kilometers long, 50 or so kilometers wide, and at least 500 meters deep. Actually, we know it's more than that, maybe even 1,000 meters deep in some places. It's a colossal lake. And of course, when we published this stuff in 1996, immediately there was interest from microbiologists regarding this as a viable and extreme habitat for very unusual life. And given that this is a lake which may have been isolated from the rest of the planet for millions of years, it might well be that whatever's living in this lake has been living in isolation from the rest of the planet, like a natural sort of laboratory of adaptation for microbes. And also the sediments on the floor of that lake may well contain very interesting records on climate change, starting where ice cores, which are extremely valuable for paleoclimate, where ice cores stop.
So they could take us even further back into the past.
And potentially much further back. Yeah.
And how far back did the ice cores go?
Well, the Vostok ice core goes back about 440,000 years.
Wow.
The ice core,
we can tell the CO2 levels and...
Yeah, it's been brilliant. The Vostok ice core is an amazing thing which tells us about carbon dioxide levels over glacial cycles and methane contents and other such things. The ice core at Dome C, which is not so far away, goes back about 770,000 years, I think. And there is some thinking that we can probably get back to 1 million years with ice cores, maybe 1.5 million. That might be wishful thinking, but certainly 1 million years. So there's a big hunt for 1 million-year-old ice in Antarctica at the moment, which is a great thing. But regardless of that, what's in the sediments will start where that ice stops, and it can potentially take us back many hundreds of thousands, maybe millions of years, much further back in time.
And so we'd like to get the sediments. And actually, you were involved with a big, ambitious trip that I mentioned at the beginning of the interview to Lake Ellsworth. Can you tell me about this? So this took 10 or 15 years of planning to make this expedition happen?
So when in 1996, when that big paper on Lake Vostok happened, people were interested about subglacial lakes and how we're going to get into it. And there was a lot of international debate. The Scientific Committee in Antarctic Research put a big team of people together to consider how we're going to do it. And then there was this extended episode of discussions with engineers, with microbiologists, with geologists, sedimentologists, ocean people, about what kind of program needs to be configured, because nothing like this has ever been done.
What needs to be configured to actually explore?
Yeah, you need a number of things. You need work out exactly precisely what science you're aiming to do. So there's a scientific experiment that needs to be designed. Work out how you're going to do it. So there's an engineering challenge about how you're going to get down into the lake. There's an environmental protection issue, because these are pristine environments and we don't want to contaminate them. But also the experiment that we'll be trying to do is likely to be measuring very low levels of life and chemicals and nutrients and things. And so we have to keep the experiment really clean to do it. And there's a massive logistics challenge as well. And at the time, we need to work out where we're going to do that experiment, because Lake Vostok is this massive subglacial lake, but it might not necessarily be the best lake in the first instance to go to. So there was a lot of thinking around this, and a program that I and colleagues came up with was an exploration of Lake Ellsworth in West Antarctica. We chose West Antarctica because the elevation of the ice sheet is a little bit lower than in East Antarctica, so the environment's not so harsh. The ice is much warmer than in East Antarctica, so drilling down through it is a bit easier, and logistically it's easier to get to as well. We mapped out the lake, so we did a high-resolution geophysical survey of the lake, revealing that the lake was there and what the water depth was. So it's about, if you know your English lakes, it's about the size of Windermere, about 10 kilometres long. It's about 3 times as deep as Windermere. It's about 150 metres deep. But apart from that, the topography all around it looks just like the Lake District. It sort of tells us that when the West Antarctic ice sheet was not there, this lake and the topography around it would have been subject to much smaller dynamic forms of glaciers and small ice caps. And it's that erosive capability of a small glacier that occupied its valley that caused the overdeepening to happen. And then as the ice sheet subsumed it and grew very large, that over-deepening remained and filled in with water as a consequence of the melting of the ice sheet. So it all makes a lot of sense. And we did a thorough geophysical survey, and we really did know where the best place to drill into it is.
And so after years of planning, you gather various engineers and scientists together, and so you actually head down there. Can you tell me about what actually happened?
Well, the long and short of it was our experiment didn't work, and so we went to Antarctica with a bespoke drill to drill down through 3 kilometres of ice to get into lake. We had a lake probe that was going to go in, collect water samples and sediments, and it was a beautiful thing. And we had very well considered environmental protocols. So the full concept of the program was...
Like in terms of sterilizing everything?
Everything was, so we're pasteurizing the water, biofiltering the water.
And this was, so you were drilling down by heating up water?
Yeah, a hot water job, that's right. So you have a project that doesn't work out, and I'll explain why it doesn't. A lot of people think, well, that's the end of it all. But actually, in Antarctic science, it's kind of a normal situation that you have a program that just doesn't work out in the first instance the way you do it. So what you have to do is understand what went wrong, and work out what the lessons of that failure are, and work out whether you actually can solve them, because it might well be that, having worked out what these lessons are, actually you didn't appreciate it at the time, but you can't solve these things. You can't do what you tried to do. Turns out with our program, what we had to do, the technique in hot water drilling, is, it sounds a bit sort of trite, but you need a lot of water to drill through 3 kilometres of ice, and it's too much water to create at the ice sheet surface. So what you have to do is create a little bit of water at the ice sheet surface, about 70,000 litres of water.
And here you had to shovel for hours and hours into a boiler.
I'm expert at that. Yeah, in a big onion tank.
Maybe the road building was helpful.
It was definitely helpful for that. I didn't think I would be doing that type of labour in the middle of the West Antarctic ice sheet, but there I was. But you can get down to about 60 or 70 meters, maybe a little bit more than that, but you can't get down much further. So what you do with the technique is you have 2 holes that you drill. The first hole you drill down, and then you leave your hot water drill on, and you create a very big reservoir underneath the ice, and that is the water that you will use to go down much further. The technique is that you have to have a pump in that particular hose, and so you can recycle the water that you just created back to the surface, heat it up, pasteurize it, and then put it down the main borehole. Now the main borehole goes right next to it, quite close, about 2 meters away next to it. Now that was all working very nicely, and we created our first borehole with our big reservoir, and that was all working really well. But the technique that we needed to do was to link the second borehole into the reservoir. That's absolutely essential that we do that for circulation reasons and for some hydrological reasons as well. And we tried and tried and tried. We just couldn't find that link. We couldn't find it. And when you're doing this type of work, it's exhausting, because the more you're trying to find that link between the main borehole and the reservoir, the more you're losing fuel, the more you're losing your surface water, and the more tired you're getting, because you're shoveling snow all the time. And after about 36, 40 hours of doing this, we just said we can't do it anymore. We haven't got enough fuel, we haven't got enough water, and we're utterly exhausted, and that's the end of it. And so when we came out, it was a terrible thing. All the equipment was working really nicely, but we couldn't make that link. Now when we look back at it, getting back into the UK, it was a terribly disappointing.
And how does that first feel? Like you spent 12 years planning this. It's one thing to say afterwards, like, of course there are going to be difficulties, and oftentimes in Antarctica you don't succeed on your first try, but yeah. I mean, and this was Christmas Day or Christmas Eve
it was
too,
Christmas
right?
Eve. Very late on Christmas Eve.
I'm sure not the best Christmas present you ever received.
I've often said that was. I really hope that's the worst Christmas I ever have, because it was pretty bad.
It's kind of like training for 3 Olympics in a row and failing to.
Well, I didn't get the wrong shoes or something. It was just dreadful.
Yeah.
And you're absolutely right. Now, how many times people will pat you on the back and say, the biggest failure would have been not to try, and all that sort of stuff. It doesn't really work, to be honest with you. And it takes a little while to gather things together, and then to think objectively about what it is that you did. And it needs also, it's not just about me, it's about all the team providing input into that. And so we had a formal exercise by which we did an independent assessment of the whole programme with sort of a warts and all approach, everything being open to it, all the paperwork, everything being available for external inspection, with the idea that we need to get to the details of this program to work out what went wrong, because only when we know that can we, as I said previously, work out whether fixes are reasonable and then whether we can do it again. And I should say that we're really pleased about all the help that we got with that particular review, and the advice that we got is that the project that we set out to do is entirely feasible, but we need to make sure when we do it again that we have that connection. And we thought about, well, this connection of 300 meters beneath the feet with this big reservoir of water trying to link the borehole into it, do we need to make that connection? And I was of the opinion, we just must design it so we never have to have that issue again. But there are so many reasons actually why we do need that, for circulation reasons, for hydrological balance reasons as well. But there are a number of things that can help us. We don't necessarily need to have one reservoir linkage. We could have 2 reservoirs or even more than that, and have one much closer to the surface that would help us have confidence in making that first link. We can have much more precision in the way that we're drilling down, and there was instruments available for us to do that now. All these things that we need to implement are being tried and tested in the Antarctic field now and in coming field seasons. And when they report back the successes or failures of those things, when we're really confident that not only have we learned the lessons, but we've put into practice the changes that are needed in other programs, and we've got a watertight case that we know how to do it this time, then we'll propose to do it again.
And you haven't given up.
No. It's, so when
because this could have big implications, both, as we said, for climate change and for life. For these lakes have been isolated for so long.
This is blue skies, curiosity-driven research. There are very good scientific reasons why we want to do this work. My prediction is that in 50 years' time, we will have examined and explored and understood many subglacial lakes in Antarctica. But to do it, you need hot water drilling, you need the experiment that we designed for Lake Ellsworth, and you need to be repeating those things. So the lessons that we are learning and have learned and have published, I wanted to be publishing papers on the scientific discoveries, and I've ended up publishing papers in the last couple of years on all the things that went wrong and how to put them right. But those are important things to do, because whoever, if it's us or whoever it is, needs to understand our lessons to learn. And through the work that we've done, I hope, and I anticipate that it will be this case, that other programs will be in a much better position to do those things. So in 50 years' time, we'll look back at the episode at Lake Ellsworth as being a necessary failure, because these things that we learned the hard way had to be learned at some stage. And even though it takes some swallowing, unfortunately, we didn't want to be in this situation. We wanted to be highly successful. Of course, all scientists want to do that. But when you're in the position that we are, the only thing you can do is to take a very positive attitude to what's just happened.
So we mentioned why the Antarctic matters for climate change. Do we need to be worried about the East Antarctic? So we know the West Antarctic is going to pose us trouble. What do we know or not know about the risks or the vulnerabilities of the East Antarctic?
Well, we're getting to know and appreciate a lot more about Antarctic change as a consequence of satellite information. The satellites have been monitoring the surface height of the Antarctic ice sheet for maybe 30 or so years. Different satellites have been doing that, and they all point to certain bits of Antarctica losing mass. And that's actually verified by gravity data as well. Most of it is in West Antarctica, but it's not exclusive. The change isn't exclusive to West Antarctica. There are parts of East Antarctica that are changing too, and in particular a place called Totten Glacier, which looks remarkably like the West Antarctic ice sheet in terms of its topography. The thing about Totten Glacier is just that glacier itself, its whole catchment, contains as much ice as the whole of West Antarctica. So this is a glacier that we are particularly concerned about. And it's like the Totten Glacier itself is just a little bit on the ice sheet edge, but its catchment is very large in the ice sheet. So Totten Glacier basically acts as a plug of this whole expanse of ice.
So if that goes, then the whole...
Yeah, we're worried about it, and we're worried about the change, and we need to understand how change in Totten Glacier will be translated backwards into the ice sheet, and how the ice sheet will become mobilized as a consequence of the change in Totten Glacier. A few years ago, we knew nothing about the topography of Totten Glacier. It's one of those areas of topography that we had very little idea about, but the work that I've been involved in, again with Australian and American colleagues, has mapped out the topography in that region and has uncovered this as a really vulnerable part of the ice sheet.
I imagine when you study the ice sheets, there's two things. It's scientifically, I'm sure, very interesting. Like, as you say, it's a new frontier in many ways. It's one of the last places on Earth that we don't understand that much about. But at the same time, the implications are so dire. Are you able to separate those, or when you're doing this research and maybe come across something worrying, do you first think, oh, this is really interesting, or oh, we've got to watch out?
Scientists are always really good at making the most of their results, I find. And so we're always keen to understand. It depends on what community you're speaking to. So some of the work that we've done on Totten Glacier has been concerned about what the potential sea level implications of these things are. And it's important to get that information out because, as I said, it's about the size of the whole of West Antarctica. And so that's important to know these things. But with the same data, we're also understanding the more sort of nuanced and detailed processes of the way that ice flows and the way that water flows underneath it, which might not necessarily be of interest to a big sort of public audience, but from a glaciological perspective, it's still new knowledge that helps us build better models of the way that the ice sheets flow, which makes us make better predictions of the future. So all these things are part of any scientific program, I think.
As we get towards the end of the interview, I think Antarctica, it feels remote. It's hard to worry about in some ways because it just seems so impossibly far away from our day-to-day experiences. You said something interesting when I was researching for this interview, and kind of scary, that because of gravity impacts, it's actually in the northern hemisphere that from this melting water that sea level is actually going to rise the most. Can you explain the reasons for that?
Sure. In the 1970s, it was appreciated that the big ice sheets around the world, Greenland and Antarctica, have such a large mass that they have a significant gravitational attraction, so the sea level around Antarctica and Greenland is artificially high than it would be if the ice sheet was not there.
So it actually kind of pulls water a bit to
water. So the funny thing is that if you got rid of all the ice, say in Greenland, sea levels on the margin of the Greenland continent, they don't go up, they actually go down, because you lose the gravitational attraction.
So because all the water melts, the gravitational effect
goes... It's not there anymore. The gravity effect is not there because the ice sheet's gone and it's all been distributed around the ocean. So the sea level goes down around Greenland. It turns out in the UK, the further away from Greenland you go, because that effect, the gravity effect, is relative to the fourth power of the distance, around about the UK, it doesn't really make much difference. So from a very selfish perspective, if the Greenland ice sheet decays, well, we don't really care about that in Britain. There's probably other reasons where you might want to care, like the whole shape, the orography of the planet, and the way that the storm tracks might flow. But from a sea level perspective, we're not too worried. But in Antarctica, because we're so far away from Antarctica, we in the Northern Hemisphere, in the UK and other parts of Europe, we will see the maximum influence of sea level implications from melting of the Antarctic ice sheet. So even though, as you say, it is a remote place, it is somewhere where we're still exploring. It seems like an otherworldly place. The changes in Antarctica are going to be felt in the other part of the planet, i.e. where we are right now. And that is why we all should be taking notice of the Antarctic ice sheet.
And is the sea level rising right now? I mean, because of this melt? Can we attribute some of the small changes in sea level rise to the melt going on?
So most of sea level rise that's going on around, it's about 20 or so centimetres since the records began in the middle of the 19th century or so, and predictions are going to be somewhere around 50 to 80 centimetres over the next 100 years. So it's increasing, the rate of change is increasing. Half of that is due to thermal expansion of the oceans. So the oceans are getting warmer, and as a consequence of getting warmer, the ocean water expands, and so sea level rises as a consequence of that. Slightly under half of it is because of the glaciers that are melting on the planet. But the Greenland ice sheet contains enough ice to raise sea level by 7 metres. West Antarctica is 3.5 metres. East Antarctica is 57 metres. All the other glaciers, all around the world, and there are hundreds of thousands of glaciers, put them all together and melt them all, you get 50 centimetres of sea level change. And so in terms of future sea level change, even though glaciers, we don't want 50 centimetres of sea level change, it's the big polar ice sheets that are going to cause the biggest influence on future sea level change. And that's the biggest uncertainty in our predictions of sea level change come from what's going to happen in Greenland and what's going to happen in Antarctica. And there is potential for many meters of sea level change in the centuries that are ahead of us. And our problem is we may be locked into those changes. I don't know any glaciologists that don't believe that sea level is not going to increase in the future. And the biggest unknown that we have is the reaction of Antarctica and Greenland to ocean and climate warming in the centuries that are ahead of us, and the unstable internal ice dynamic response of all of those things as well.
And just to end off, I mean, looking forward, do we have a sense of when they might become unstable? At what level of warming? We all hear about the 2-degree target. Hopefully we're going to get the world underneath.
So one is this unstable reaction to processes which are going on right now, i.e. in West Antarctica, and the marine ice sheet instability, and that might be happening. But it will take centuries or maybe millennia for that to happen. And we can tell it takes some time because the Ice Age took about 10,000 years for all the 7 or 8 degrees centigrade of warming, and it took about 10,000 years to get rid of all that ice. So it takes some time, but it is inevitable that it happens. And sea level rose from the Ice Age to, when it was 10,000 years ago, the start of the Holocene, by 120 meters. Right? So that was natural climate change causing a big reaction. So what I take from that is it's entirely possible that sea level can go up by several meters. It might take some centuries, but it's inevitable that it will happen, and we're going to have to deal with that. Where's the ice that's going to come from? Well, it's in Greenland and it's in Antarctica. And where's the evidence that it's happened before? Well, it's in the last ice age. So what we're doing at this moment, this amazingly stupid experiment with our planet and warming it up, well, we pretty much should be no surprise at all that the ice is reacting to that change, and the sea level is going to go up as a consequence.
And I guess the higher we let it, the temperature get, then the greater the risk that the whole system will become unstable.
Again, you can go back into some time. So we're heading in a world where already over 400 ppm of carbon dioxide in the atmosphere. When was the last time that happened? You've got to go about 3.5 million years into the Pliocene. In the Pliocene, sea levels were 5, maybe 10 meters higher than they are right now. That's because there was no Greenland ice sheet and there probably wasn't a West Antarctic ice sheet. And that's because that's the natural Earth system in a world with 400 plus ppm. Where we're headed even further, if we don't do anything about it and we go over 1,000, right, which is sort of the worst case scenario predictions for the end of the century, then you're going to have to go back something like 60 odd million years, where there were dinosaurs around on our planet, and Earth was much, much warmer. So these are stark lessons to learn from geological history about what the world is like when carbon dioxide levels are at certain values, and what the ice sheets are like and what the sea levels are like. It doesn't happen instantly, right? Geologically, it's quite quick. It happens over centuries and millennia, but those changes are inevitable. It's like when you have an oven and you turn your oven on to 180 degrees. It doesn't instantly heat to 180 degrees, but it will do unless you turn it down. It's inevitable it will happen. And the experiment with this planet, there are inevitable consequences that we just have to appreciate. And one of them is when you warm the planet with carbon dioxide feedbacks, the ice will melt. It's a substance that melts at 0 degrees centigrade when there's more heat, and sea levels will go up. It's obvious.
Well, something to keep in mind as we head into the all-important COP21 in Paris.
Indeed.
Well, it's a fascinating area of research, if somewhat worrying. Martin Siegert, thanks so much for coming on the show.
A pleasure.
Thanks for coming, everyone. Appreciate it. Thanks for that. Yeah, that was great. And that's all for this episode of The Elephant, recorded live in Birmingham. Thanks to Climate Kick for hosting us, the CKAA for helping organize the event, and of course Martin Siegert for taking part. The Elephant is put together by myself, Kevin Caners, with Matthias Gutz and Christina Peters. A special thanks this week to Mervyn DeGanos. This episode was made possible with funding by the CKAA, a European society of entrepreneurs, scientists, students, professionals, and policy officers working to create a climate-resilient society. Find out more at ckaa.eu. You can find The Elephant online, wetelephantpodcast.org, or say hi on Twitter. Our handle is @elephantpodcast. And as always, you can find us in iTunes or on SoundCloud. I'm Kevin Caners. See you soon.